No calculator problem there. There's a bunch of my work and my answers for that. Although I do have, it looks worse than it actually is because I have two ways I worked out part D there. So you just kind of choose whichever way you like the best there. What this could be a really good problem for us, right? It gives us a function and it just tells us to show that the derivative is equal to that. And so I'm just going to write that function down. I'm just going to take the derivative. This is an implicit differentiation problem. So you take the derivative as is. If you do the derivative of x's, that's your normal derivative. If you take the derivative of y's, that's when you tag on your y prime. So I got 4y, tag on the y prime. The derivative of the number is 0. Here you have to remember this is your product rule. So we'll go first times the derivative of the second plus the second times it by the derivative of the first. When you do the derivative of y, you get your y prime, right? And then we know what to do. We move all of our y primes over on one side of the equation. We factor out a y prime and we divide. And then we're happy because it told us to show that the derivative is equal to that. And I actually got that for my derivative. So I know that I did that right there, but then all that work, that's our support, that's our answer. Part B says write the equation of the tangent line. So if it gives us a point, we know to write the equation of a tangent line, we need a point and a slope. So it gives us the point. To get the slope, we need to take that point, plug it into the derivative because the derivative is slope. So I plugged in the radical 3 for the y's, plugged in the 0 for the x's, and you just got to know cosine of 0, that's over there at 0 degrees, 0 radians. That's what that x value is, which is 1. And then the sine of 0 is the y value over there at 0, which is going to be 0. So that's going to give us a radical 3 over 4 radical 3, gives us 1/4 for the slope. Now, this is already your y-intercept, so you could jump straight to y equals mx plus b, jump straight to that. Or what always works there is your point slope form. So I did y minus the y value equals the slope times x minus the x value. X minus 0 is just x, and I just slid that over right there. You're allowed to leave that in point slope form as well. But taking the basic derivative, we should be strong at, and then doing the basic equation of the tangent line, we got a bunch of points racked up right there on parts A and part B. Okay, now part C says find the coordinates. So when I saw coordinates, they didn't want just an x value there. So I wrote down a note for myself. I'm going to need to find an x and then a y value. And then it says the tangent line is horizontal. We know when it's a horizontal tangent line, that's where the slope is equal to 0 and the derivative is equal to 0. So I'm going to take the derivative and set that equal to 0. Now, even if you happen to make a mistake and you couldn't get part A, they gave us the derivative. So you could just take that derivative and set that equal to 0. So a fraction is equal to 0 where the top is equal to 0. So I took that top, set that equal to 0. And when I set each piece equal to 0, that gives me y equals 0 and cosine of x is equal to 0. We're not using y equals 0 because this whole problem exists when it says y is greater than 0. So y equals 0 is not in that interval. So I just kind of threw that one out. And then where cosine was 0, it told us we're in between 0 and pi. So a cosine of 0, we're thinking on that unit circle, where is that x value equal to 0? So that's right there at that pi over 2. You don't care about this because you're only in between 0 and pi. So we're only going to get x as pi over 2. So we got that. But then remember, we said we wanted the coordinates. So once we get the x value, we need to also figure out the y value. So if I want to figure out the y value, we always have to go back to that original function. So I'm going to utilize that original function. And I'm going to take the pi over 2, plug that in place for the x into the original function. Sine of pi over 2 is that y value right there, which is 1. And then I had a quadratic equation here. So I had to move everything on one side, set it equal to 0. I've been able to factor that thing. So make sure you're just careful, factor that. And if there's a number in front, just make sure you multiply it out in your head real quick. Make sure it actually is equal to that. And if you need any help with the factoring, please let me know. But you're going to factor it, set each piece equal to 0. That gave you something out of the interval. And then I got that y was equal to 2. So I got my x value, my y value. And then going back to the top, I just want to stress, like I said, a fraction is equal to 0 where the top is equal to 0. Technically, a fraction is equal where the top is equal to 0 and the bottom is not equal to 0. So at that x equals pi over 2, I did plug that into the denominator, where I plugged in that point to the denominator, that 4y minus sine of x, and I got that was equal to 7. So, like if you got 0 over 0, that's like L'Hopital's rule, indeterminate form right there. So that was just a little technicality. I just double checked that real quick. But yeah, you shouldn't have to worry too much about that. But taking the derivative, set it equals 0, because you see that word horizontal, that's worth something. And then getting into the actual x values worth some other points there. And then finding the y value would be worth the rest of it. All right, now it says at that point, for letter D, it says at this point, we got to determine whether it's a relative max, relative min, or neither. Now, we already discovered at this point that's where this derivative is equal to 0. So that means there is a possible relative max or relative min right there. So there's two ways that we can actually check for this. One way, which is a little bit less work, is using your first derivative test, right? Where we're checked to the left and to the right of that pi over 2. So I'm in between 0 and pi. Pi over 2 is the point in question. So I just took the 0 and the pi and I plugged it into our first derivative. And I'm just trying to see, does the first order change from positive to negative or negative to positive? Just like when we did our X, Y, Y prime charts earlier in the year there. So if I took 0 and plugged it in, F prime of 0, we kind of did that right here. When X equals 0, that Y was that square root of 3 number right there. So I was able to plug that point in. I got 1/4 for that. And then when I did F prime of pi, I was able to plug in the pi for the x's there, and that's also going to be the square root of 3 for the x value. I'm sorry, for the y value. Let me go back and backtrack right there, make sure we know. So when I did f prime of 0 and f prime of pi, I think I might have made that a little bit confusing. So when x equals 0, I'm going to go up here real quick there. When x equals 0, I'm plugging in a 0 for that x right there. So then we're going to get this 2y squared minus 6 equals y times the sine of 0. The sine of 0 is 0. And so you get 0 times something. So you basically just going to get 2y squared minus 6 is equal to 0, which is going to give us y squared. I'm going to move the 6 over, divide by 2, and then I'm going to get the y is equal to that square root of 3. And then the same thing, when x is equal to the pi, I can plug the pi in right there. So I'll get 2y squared minus 6 equals y times the sine of pi. The sine of pi is that y value right there. That's the point -1, 0, which is still equal to 0. So you're still going to run into 2y squared minus 6 equals 0, and you're still going to get the square root of 3. So that's why when I'm plugging in the 0 for the x, that's why I'm plugging the square root of 3 for the y, because I wasn't sure what that was, but when you plug it into the original function, you get that because you need the x and the y because your derivative has x's and y's in there. So if there's still any confusion on that, just let me know. But when I plug those in, I got a positive first derivative and then a negative first derivative. And then so that's why I said there's a relative max there at that point, since the derivative changed from positive to negative. That means your function is changing from increasing to decreasing, making that a relative max. That's one way we can look at that. Another way, if you didn't think to use the 0 on the pi, if you didn't think to do that first derivative test, is utilizing, it's a little bit more work there, but this is an alternate method, is utilizing that second derivative test. And that's what I got down right here. So remember what the second derivative test is. We already knew that this was our point where the first derivative is equal to 0. Now, the second derivative test on your blue packet, we got that for you here. It says if you take that point and you plug it into the second derivative, here's our second derivative test. You find where that first derivative is equal to 0, so we already have that point, and then you plug it into the second derivative. If your second derivative is positive, that means your function is concave up there. So if your first derivative is 0, your graph level's off. If your second derivative is positive, that means your graph is concave up. So it's holding water at the same time leveling off. That makes that a relative min. If your first derivative is 0 and your graph level's off and your second derivative is negative, that means it's concave down. That forces that to be a spilling the water, that forces that to be a relative max. So basically what I'm going to do is find my second derivative and plug in this point to determine whether it's positive or negative. So when I do the second derivative, I have to use the quotient rule. So I did the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. And then remember, when you're taking the derivative of y, you got to tag on the y prime or a dy dx. So I did the denominator, but then when I did the derivative of the numerator, that was a product right there. So I had to do a product rule in the middle of that quotient rule. So I got my denominator times by the derivative of the numerator with the product rule. And then I did the derivative of y, which is the y prime of the dy dx. And I did minus my numerator times it by the derivative of the denominator. So I did derivative of 4y is really 4, tag on the y prime right there. Now at that, and then it was all over the denominator squared. Now at this point, everywhere I plugged in the power 2 for the x and the 2 for the y, everywhere I saw an x and a y here. And then also whenever I saw the dy dx, at that point, the dy dx was just equal to 0. And so then you kind of see my work there. I just kind of evaluated some things there, and I was able to calculate that second derivative was -2/7, which if it's a negative, so if the first derivative was 0 at that point, the graph levels off and the second derivative is negative, that means the graph is also spilling the water right there, concave down, making that a relative max. So you don't have to call it the second derivative test, but you could just say, hey, there's a relative max, or since that derivative is equal to 0 and that second derivative is negative, those two items was also classifying that thing as a max right there. So a little bit less work here, but if you weren't quite sure, like, to use the 0 and the pi or how to get some of those values right there, then you could just kind of do that both ways to demonstrate the maximum or the minimum values there. Hedgehogs. Sonic the Hedgehog.